Okay, so last time we were kind of exploring the connections between quantum field theory and statistical mechanics. And if this thing ever loads, there it goes. We started off with I just started off with some general statements that, about the renormalizability, talking about divergences everywhere and the fact that, it's basically telling us that we're ignorant of what happens at high scales. And high energy scales correspond to low or small distance scales. Right? So there's this type of correspondence between high energy in QFT and low energy in condensed matter, like what we'll see. So ultimately, we'll get to a section where we'll talk about the, kind of a deeper understanding of where these divergences come from. And this was kind of mapped out by Ken Wilson, I think back in the 60s or 70s. But we'll get there soon enough. But first, we wanted to talk about some condensed matter physics, right? And we, in particular, were interested in this phenomena of second order phase transitions, right? So these kind of discontinuous transitions. And we've talked about, like, for example, a ferromagnet. We also said that there's numerous examples of this type of phenomena in condensed matter, whether it be liquid helium or whatever. And we talked about how these transitions occur, right? And, when you think of these transitions on a large scale or, kind of a zoomed out scale, you can kind of map out, this individual behavior of these, electrons in terms of a field, right? A field density, right? So you can talk about the spin field, right? And that was the approach that Landau took when he was trying to describe all of this. I'm trying to get to that part, right? So this is all stuff about condensed matter or stat mech that I don't want to discuss. But so he started with the Gibbs free energy equation. So he's talking about, trying to describe the behavior of some metal, the magnetization of that metal in, an external magnetic field, right? At what point, in the temperature or in the magnetization do you, have these phase transitions? So he started out with the Gibbs free energy and noting that, the critical behavior happens around some critical temperature and where the magnetization is basically zero.
It's first order transition.
Yeah, this is first. So this would be first order here. The transition across this line.
Right.
Right. Second order transitions where you come in this way.
By transition, you mean the magnetization?
Yeah. Yeah. Yeah.
So we are interested in second order.
Mm-hmm. Yeah.
When that happens.
Yeah.
It's first order when second order transition happens.
No, that's what I'm saying. The first order transition is down here at low temperatures, right? And you vary the magnetic field, and you get this flip in the magnetization. It's either greater than zero or less than zero across this line. Second order transitions when you come in along this kind of this area right here, and you get that bifurcation of you could either go one way or the other. You understand what I'm saying?
Yeah.
Yeah, that's the difference.
The Wikipedia.
Yeah.
Says something else.
Oh, okay.
You're changing two variables, and then
Right.
until something happens discontinuously. So the variables we're changing here are like H and T,
Right.
and so that's what makes the second order. That we have two parameters that change.
Yeah, the Wikipedia says the first, it says it's the magnetic susceptibility. The magnetic susceptibility is second order of the changes discontinuously. But here says the magnetization is which is the first order derivative of the energy, increases continuously.
From 0
To the
ionization, which is the first derivative of free energy. Increases continuously from 0 as the temperature is lowered below the free temperature. As we, yeah, I mean, well,
actually, this doesn't make sense.
yeah. Is it talking? I mean, is that talking about first order or second order transition?
It says it depends on which physical quantity you want to consider. If you want to consider the magnetic susceptibility, that's the second order transition. But the magnetic field,
What's is it? I don't know. What's the difference between magnetization and magnetic susceptibility?
Isn't it related with how easily the arrows turn?
yeah,
And so,
yeah, it seems that both of them have to be related.
yeah,
Yeah.
they're related somehow.
Yeah.
Because we're looking at pockets of arrows. So somehow the susceptibility is changing with time. Some other
Yeah. So I don't know if I answered your question or not.
Yeah, I may be very more to ask my question than that.
Oh no. Well, I should probably know, but
But the thing that you're saying makes more sense to me
Mhm.
than it because it's contradicting each other.
Yeah. yeah. I
one.
don't.
Wikipedia tends to be like overly technical too on some articles.
Well, yeah, because you have people that just sit there and
Yeah, like that's all.
edit articles, you know. And if you're that kind of person, you're probably
Yeah.
really technical. I used to have an office when I was at the National Lab next door to a guy, and every time I'd walk into his office or walk by his office, he was on Wikipedia writing articles.
Good for him.
Yeah. I mean, he obviously had tenure or whatever, you know, the equivalent is at National Labs. But okay, so let me see if I can get down where we were. Okay, so whatever a second order phase transition is. Okay, so here we go, right? And so the way that Landau approached this thing was that, you know, we're at low values of magnetization or magnetic susceptibility, we're not sure. And the temperature, so you can expand out the Gibbs free energy in these parameters, right? And so you plug that into the Gibbs free energy equation, and he finds that, you know, for temperatures greater than TC, you have this kind of just this trivial solution for the magnetic field or for the magnetization, where it's minimized at m equals 0. But below that temperature, you actually get a behavior where the local minima are now non-trivial. They're out, you know, at some finite value that's non-zero. Okay, and so the transition from this to this is second order phase transition. That's all. That's as a particle theorist, that's what I know. As far as condensed matter, I mean, I don't know. So he took this a little further, wrote out, so he kind of, parameterized this behavior by defining T in terms of the difference between T and TC, and C is just some constant. And you can show that, for certain, or for certain temperatures, above TC you have just the trivial solution, and below TC you get these non-zero solutions. And then you can go on, you can add in an extra magnetic field, so on and so forth, right? So he said, okay, so to study these this type of phenomena, it might be better to introduce this spin field or spin density field, and then write the magnetization in terms of a volume integral of that. Right? And if you do that, and then you plug that into our equation that we had earlier for the Gibbs free energy, you get something that looks like this, where we noted that this del S squared term is kind of a shearing term, so it's possibly the interaction of these bubbles of different polarizations, and that we use the fact that these guys are small, and so we are able to neglect so that we can neglect the S of the fourth term, right? And then we use something kind of analogous to the principle of least action. So we take the variance of the Gibbs free energy, and we assume, we enforce that has to vanish, and we go through some mathematics, and we get down to something basically in this equation 13 that looks like the Klein-Gordon equation, right? Where instead of our field phi, we have S, okay? And on the right-hand side, we have some source term, right? So before, for our Klein-Gordon, we would have had 0 over here, right? But this is for the case where you have a source, okay? So you can see the parallels between, the theory that we basically use to describe the Higgs and, the theory of some phenomena in condensed matter. Right? So it's kind of interesting that the two are really related. So you can introduce. So what he did was introduce a magnetic field at the origin, right, using a delta function. And in that case, you find the spin field is just the Green's function of that operator on the left-hand side. You can solve you can do the integral for the Green's function, and you get something that's exponentially damped. And actually, it looks like the Yukawa potential, right? It goes like 1 over r and then e to the minus r, right? Which is what we talked about. It's kind of a screened Coulomb potential, right? And this parameter c is what they call the correlation length. So basically, kind of gives you, what's the word I'm looking for? Kind of the scale of these types of bubbles, that you get in these transitions. Did I get to this point? Yeah, I got to this point, right? So it turns out that, he uses to describe the behavior of ferromagnet, but you can use the same theory to describe, all these different phenomena, whether it be liquid helium or, what was the other one? Binary alloys or something like that. But all this different behavior, right? Okay, so we've seen, this connection kind of between statistical mechanics and QFT, and we're going to take it a little further today, okay? And so I ended last time by telling you that, we're going to draw comparisons between the generating functional and the partition function of stat mech, right? And I don't know if it's, I don't think it's it's a coincidence that they're both labeled as Z. So for us, for a general, scalar field theory, we would write down a generating functional that looks like that, right? Equation 20. And we know that the time integration that's included in that d4x goes from minus t to plus t, where we always take minus and plus t to minus or plus epsilon. But we found that if we actually let those parameters go slightly imaginary, that we could take the initial and final state both as the vacuum, right? That was the whole reason behind introducing this, plus or minus I epsilon, okay? And then from that, we can always construct, observables like, correlation functions, time ordered products of operators by taking functional derivatives, okay? And so, like I said, the generating functional is very reminiscent of the partition function because you do the same types of things, right? You get in StatMech, from what I remember, you write down the partition function for whatever your system is, and then you can compute observables by taking derivatives with respect to whatever variables, like the pressure, or the magnetic field, or whatever, temperature, right? So it's the same kind of idea. And you can make it a little more concrete, this connection between the two by playing around with the time integration of the generating functional, right? So basically what that I epsilon does is, we're integrating along the time axis, and if we shift it by plus or minus I epsilon, it kind of, tilts it into the complex plane, right? And that starts to sound like what we did for when we were computing loops, right? We had the integration over the time variable, and we said, well, there's poles, but we can rotate it onto the imaginary axis, which is called a Wick rotation, and that allowed us to get something that instead of had this Minkowski metric, had a more Euclidean metric, right? And so we can use the same type of trick here, and so we'll redefine the time integration, right? So we'll rotate it onto the imaginary axis, right? So it takes us from Minkowski type measure to a more Euclidean measure with this minus sign, overall minus sign. Okay. All right. So let's see how this works for phi to the fourth theory. Okay. So we have our Lagrangian plus our source term, and I plug in my Lagrangian, and the only allowable terms or normalizable terms are the kinetic energy, the mass term, and then this phi to the fourth term. Okay. So now let's take this and Wick rotate it. So if we Wick rotate it, two things happen. So from the dx naught or dt integration element, we pick up a factor of I. So we're rotating onto the imaginary axis. And then anywhere we have phi squared, we pick up minus signs, right? So, not phi squares, but where we have dot products. So in this kinetic energy where we're taking del mu, we pick up an extra minus sign because we're in this kind of weird negative Euclidean space. All right. So what that does is it flips, if you pull out the sign and stuff, it flips some stuff around, right? So we end up with something that looks more like this. Okay. And now what you see, if you look up at the Lagrangian, just the Lagrangian, so forget about the source term right now. This looks more like a Hamiltonian, right, or more like energy, right? And so you can actually, you can actually say, okay, I know for certain that this thing is bounded from below, right? And for the Lagrangian, you never know because you have this minus sign in front of the potential, right? And so what it means is that this exponential here is very similar to the way you'd write the partition function down, right? Because now you have this statistical weight from this exponential, and that kind of determines the fluctuations of your field. Right? And in this form, the kind of the connection between our generating functional and the partition function from StatMech is almost exact. Yeah. Okay. So we can go on and compute the the Wick, after the Wick rotation, we can actually calculate the Green's function. And for the case for free theory, which is a lot simpler, we get something for a 2-point function that looks like equation 26, and we can actually say, well, this is going to have, as k goes out to no. Say, but the point is that you can approximate this integral as this kind of dying off exponential, and it's kind of the four-dimensional analog of what we wrote down in equation 18, which was, I think, that Yukawa looking. No, yeah, it's that Yukawa type behavior of the spin field. Okay, so we're in quantum field theory now, but we see that after doing this Wick rotation, we can do this compute the Green's function, which is basically a 2-point function, and we see the same type of damped behavior, right? So what we've seen is basically that this scalar quantum field theory is a very close analog to the continuum description of ferromagnet in terms of the spin field. Okay. Yeah. So we have this tight connection, okay, and what we've seen is through this Landau type of analysis that through these second order phase transitions you can go from boring old parabolic type potentials to potentials that have non-zero minima, right? And so what you can ask is, well, we've got this correspondence. Could something like that happen in field theory, right? In scalar field theory. And it turns out that the answer is yes. Okay, we have now. When I first started teaching this class, we only had one proven example, but now we actually have two, right? So what happens is that what was I going to say? I don't remember. But anyway, so this behavior in quantum field theory goes under the name of spontaneously broken symmetries or hidden symmetries. We have two examples of it in nature that we know of. One is the theory of strong interactions. So this is where you, at very high temperatures, right, you can have a quark gluon plasma, right? So you have free quarks and stuff like that. But then you cool down below some temperature, and now the quarks and stuff start to bind together, right? And you can describe that using this idea of spontaneous symmetry breaking, which we're going to talk about, but I just wanted to introduce it. Okay. And then the second and the most well-known example of this in field theory is what we call the Higgs mechanism. Okay, and that's what's responsible for giving particles mass. So the W and the Z boson, how they get mass. Okay. All right. So let's see how this spontaneous symmetry breaking works. Okay. So we start off with our normal 5⁴ theory, right? With this 5⁴ interaction. And the first thing we note is that there's only even powers of the field phi, right? So there's this invariance under the transformation of taking phi to minus phi. Okay, so keep that in mind. Right, so we also see that with the potential the way it is, if we try to minimize that potential, we're going to find that the minima is at 0 for the field phi. Right? So in other words, we're going to have just this kind of parabolic shape of our potential. Right? But Peter Higgs, after probably reading Landau's paper or reading about that type of approach, said, well, maybe the same thing can happen in field theory, right? So maybe, remember how Landau kind of encoded that behavior in that B coefficient, right? He put T minus TC And so whenever t was below tc, you got this kind of minus sign, right? So Peter Higgs imagined, a scenario where instead of this term, the mass term having the usual sign, which is minus 1/2 m squared, you could replace that m squared with a new parameter that has an overall minus sign, and you call it mu, right? So minus mu squared, okay? And in that case, the Lagrangian is not describing, it's just describing a field, but the field has no mass because that term can't correspond to a mass because it doesn't have the right sign. So it's just some, it's a massless field that's propagating, and it's got these two interactions. One's a 2-point interaction, and one's a 4-point interaction. Okay? Right. Well, it's not the Higgs yet. This is just a scalar field.
So getting to that.
Yeah, we'll get there. But yeah, it's yeah. Okay. We'll see how that works. Okay, so he's making this replacement of m squared to minus mu squared. And so what does that do? Well, it changes the sign of that second term, which I'll not call a mass term, but it changes the sign of the second term. This term stays the same, right? And what it tells you is that if you try to minimize this, you don't get 0 anymore, right? You actually get two values, which we'll call the VEV, the vacuum expectation value. So it's plus or minus this combination of 6 over lambda square root times mu. All right. So we have two possible minimum, right? In this simple theory of one scalar field. Okay. So we have a potential that looks like this, right? And so what we do whenever we have a potential that has that shape, we shift out to the minimum, right? Because we want to expand about the minimum of the potential, right? And so what we have to do is, that's what we're going to do, but we have two choices. Right? Which choice do we take? Do we take, do we go to the left or do we go to the right? Right? Well, let's just choose one, and let me go to the right, I guess. All right, we'll take the positive one. And so that means I need to shift the field, right? So I need to shift the field from being phi to being out here, and we're going to call it sigma. So phi is really v plus sigma, okay? So sigma is my new field, and it lives in this trough right here, okay? All right, so let's take that and plug it into the Lagrangian and see what happens, okay? So we plug it into the Lagrangian. Everywhere we had phi, we plug in v plus sigma. Right? And the derivatives, v is a constant, so those go away. What else happens? We get something that looks nasty when we square everything out. We have sigma to the fourth, sigma cubed, and then sigma squared, and even sigma to the first power. Well, when we group everything together, what we see is that the coefficient of the term that's singular in the sigma field actually vanishes, right? Because mu squared, we've already computed by minimizing the potential, and we saw that it's actually plus lambda over 6 times v squared, right? So that term goes away, and you get some other cancellations if you plug in mu, or the expression for mu, or if you work the other way around and plug in for lambda. Either way, you end up with this piece, this Lagrangian. That's all that's left, besides some constants that I just got rid of because all they really do is change the scale. Okay?
Does the sigma have to be invariant under sign?
No. And that's the whole point, right? Because you originally had this symmetry in the Lagrangian that if I took phi to minus phi, yeah, right? But when we made that choice, remember we had that choice of which way to go. Did we go to the left or we go to the right? When we went to the left or right, we broke that symmetry, right? So that's where the spontaneous breaking of the symmetry, the breaking part of that comes from.
Now it has the correct sign.
Yeah, so what happens is now you have a Lagrangian that describes, it's still a scalar field, it's got a kinetic term, but now has the correct sign for a mass term, right? And the mass of this guy is 2 mu squared, right? What's mu? We don't know, right? We don't know what it is. It's just a parameter in the theory. But now this thing has a correct sign that we can interpret it as a mass term. And the other interesting thing is that in addition to a quartic type interaction, you find that you have a cubic type of interaction. Okay, and that's the guy that that's telling you that the symmetry is broken, right? Okay, so this is what if we had a theory like that where the mass term had a minus sign, this is what it would look like to us in nature. If we went and did measurements, we would have these scalar fields, and they had masses of 2 mu squared, and they had cubic interactions and quartic interactions, right? But then we can, through the measurement of these coefficients, you can kind of work your way backwards. You can kind of map out, there's certain relationships between these coefficients of these interactions that will tell you that you're in a spontaneously broken theory, right? Because they'll have some, just prescribed relationship between those couplings, right? And so that's what they're doing now at the LHC. Right? So they discovered the Higgs, or discovered something that looks like the Higgs, but we don't know for sure because we have to go and measure, couplings, right? And those couplings, if they match, the values of the standard model, that starts to tell us that, okay, maybe the Higgs mechanism is right? That we can work our way back now and find whatever, All right, maybe there's going to be corrections to it. It's not just going to be a straightforward Higgs potential. Maybe, something weird. Okay. But that's the whole reason that, you go off and you measure these couplings precisely, because it's going to tell you what the true theory is. Okay. Okay. All right, so we've already pointed out that the original symmetry is gone, right? But you can trace it back to the fact that we chose the VEF to expand around, right? We chose to go to the right to the direction of the right. Okay. You can actually generalize this. So we talked about one scalar field, but you can generalize it to n scalar fields, right? Where you have these phi I squared, so you're dotting phi I into phi I, right? So this is that theory where we have, a vector of phi fields, right? So there's n phi fields inside this vector, and we're dotting them into each other. Right? And we've already noted that this thing has a symmetry, and it's this type of rotational symmetry, right? We can always rotate the vector, change the indices, and nothing changes, right? And so we have this type of rotation. It's an n by n orthogonal matrix, and it's just the analogy. The same thing as rotations in 3 dimensions, but now we're in n dimensions. Okay. So again, you can write down the normal. I don't know what I wrote here. Okay, so here I've already changed the sign of the mass term. You see it's plus. Okay, so I'm writing down a scalar field theory that has the wrong sign mass term. All right. Okay. And so what you find is that now, when I minimize this thing, I don't just have this simple kind of 2-dimensional plot. I have like this 3-dimensional thing, right? So now I have, basically infinite choices that I can make, right? When I go to shift the field, right, to minimize, to expand around the minimum of the potential, I've got a lot more choices, right? And just another note, because, basically we're just putting this in by hand, right? And so, one of the mysteries is, why does the Lagrangian have the wrong sign? Okay, and that's something that SUSY can actually, supersymmetry can actually explain. It's because basically when you calculate corrections to this parameter and you get above some scale, say I don't remember what particle it is, but I think it's the stop, the supersymmetric top forks. But once you get above that scale, it'll flip the sign of mu. So it actually drives mu negative, which will give you a positive mass term. Okay, or the correct sign mass term. And that's the only theory that I know of that can do that. I don't know if extra dimensional theories can explain where that sign comes from, right? Because it's not, it's not what you would expect. Right? Okay, so in this kind of continual, field space, we have something that looks like a wine bottle, right? The bottom of a wine bottle, or Mexican hat potential, whatever you want to call it. Okay, and we find that the value of the minimum in this case is just mu squared over our lambda, right? Or the VEV squared. But this again only determines the distance from the origin. Right? In this case, it's a radial length, right? Because you can go in any direction, right? And so what we want to do is shift the field by this radial length, okay? And like I said, you've got n choices to do it, or really infinite, because you could actually, you don't have to go out along one of the field, axes. You could actually go, in between one. But the physics would not be this, would not change, okay? So what's typically done is we shift the field in the nth direction. Okay, so we leave. Let's go back to this picture. Right. So if I have a bunch of phi's, right, I would choose to say let me shift out along phi to n. Okay, it simplifies it because you're only shifting. You're only changing one component of this n component vector. Right, but you can show that, and maybe this will be on the final exam, I don't know, that if you, spread them all out, right, if you split it up, between all the n, you'll still get the same physics, okay? So this is a lot simpler, all right? So what we're going to do is we're going to shift our field, okay? We're going to shift the original field by this VEV in the nth direction, okay? So in the nth direction, we have what we had before. We got V plus sigma. Right? In the n-1 first components, the field doesn't change, right? But we're going to give it a new name and just call it pi, okay? And the pi is because this is the original theory behind, the formation of pions, okay? Or bound states of quarks. Okay. Okay, so now we can do the same thing we did before. We can take this expression for the field, we can plug it back into our original Lagrangian. Okay. And the same stuff happens. I'm going to skip all the algebra, but the same stuff happens. So you get, you get a kinetic term, you get a sigma squared term, a pi squared term, you get linear terms, but the coefficients of those conspire to cancel each other off, so there's no linear terms of the field, right? And you end up with a Lagrangian that looks like this, okay, plus some constants that I've just dropped. Okay, and you look at this guy and you say, okay, so I started with, basically a massless scalar field that had some weird quadratic interaction, right? But I shift, by the VEV to, when I minimize the potential, and I end up with something that looks like this. So I have the kinetic term for the pion fields. I have a kinetic term for the sigma field. I have a mass term for the sigma field. Right? But if I look up there, I don't have a mass term for the pion field. Okay? And that's because if you think about it, when we go back to this picture, right? So what we did was we chose the radial direction to shift the field, right? So we've broken that symmetry, the radial symmetry, right? but I don't know what do you call this? The
Azimuth.
azimuthal symmetry, if you will, is preserved, right? And that's precisely where the pion fields are. So they live in that kind of or that kind of angular part, right? Okay, so we haven't broken that symmetry, so they don't get masses. They remain massless. Okay, and so that explains why we don't have masses for the pions. But we've got a whole slew now of interactions, not only sigma cubed interactions and sigma fourth to the fourth, but we've got interactions between the sigma field and the pion fields. Right. Let me make sure I hit all the points. Right. So again, it looks like our symmetry is broken or hidden, right? But what you would do is you would go and you would measure these couplings precisely, and if they have the right relationships, you can map it back to a theory that has some symmetry in it. Right? So that massless trough, yeah. Okay. So I said everything. All right. So it's pretty cool. So we start with just some weird old Lagrangian with 5 to the 4th interaction, wrong sign of the mass term. We minimize the potential. We have to shift so we can expand around the minima, just like you would in classical mechanics, right? And we have a choice of how we which direction we go in when we shift. We typically, shift in the nth direction, right? And then that means that, the n-1 first terms, the fields don't change, but we give them different names just so that we can differentiate between those and the original phi. And the nth slot, the nth field, actually becomes a massive field with the correct mass sign, and you get interactions between these guys, okay? The really interesting stuff happens when you couple a theory like this to a vector boson. Okay? So when you couple it to a massless vector boson, right? So imagine coupling this to the theory of a photon. And what happens is during this process of symmetry breaking, you get these interactions between what here is the sigma field and the vector field, and you develop out of this mechanism something that looks like a mass term for the vector field. Right? So you can explain, the symmetry of the theory would tell you that you can't have a mass term for this vector field. That's why you don't write it down, right? But you go off and you see these vector fields that are vector particles that are massive. So you got to try to explain how that happens. Right? And that was the connection that Peter Higgs and Steven Weinberg and Salam and who am I forgetting? Weinberg, Salam, Glashow. Thank you. Right. So that's what those guys basically showed, and then they can extend it to incorporate fermions and so on and so forth. Okay. So that's where this theory gets really, this kind of mechanism gets really interesting. Yeah, so let me just touch on this. I don't want to spend a lot of time on it, but because it's not that super important. But the fact that you have massless particles when you break continuous symmetry is kind of a general result. It's known as Goldstone's theorem. And those massless particles that remain after the spontaneous symmetry breaking are called Goldstone bosons, right? And depending on the number of fields in your theory, and the symmetries and whatnot, you can predict how many massless particles you're going to have, right? And so for a case where you have n original fields, you predict that you're going to have n-1 massless fields. And that's exactly what we had before, right? Where we started out with a vector with n fields, we got one in the n that's massive, and the n-1, the rest of them are massless. Okay. Right. And so Goldstone bosons are technically they're not physical. Right, we'll see this next semester. They're not physical particles, but they play a very important role. Okay, because what's going to happen is I'm going to give you a spoiler alert, but it's okay. You're going to forget it by the time we get there. When you couple this thing to a vector field, right? You break the symmetry, you get a massive scalar field, and then you get these Goldstone bosons floating around. What happens is those Goldstone bosons get eaten by the vector fields, and that's what gives the particles mass. Okay, so it's they call it get eaten. I think it was around the time that Pac-Man was popular, but basically, what happens is you got the Goldstone bosons, and they combine. Uh, I'm trying to think how to say it. You can transform the vector field in a way that, the scalar field in a way that a lot of those Goldstone boson degrees of freedom. So you got n-1 degrees of freedom, and you can modify the scalar field where some of these guys get absorbed by the vector fields, basically. Okay, we'll see how it works, but that's the importance of Goldstone bosons. And this is just a proof. I'm not going to go through it because it's not that important. Okay, let me take a 2-minute break and get a drink of water, and we'll pick it back up.
주변이 있어. 되게 건강이 있어.
All right. Actually, what I think we're going to do is today will be the last day of class, and I'll give you guys Tuesday to study.
Okay.
Does that sound cool?
Yeah.
Okay. Because I just want to touch on this a little bit, and I put up another set of notes, but we can talk about it next semester. Okay. It's not anything, super, well, it's important, but it's not important for this summer, okay?
Are you gonna be available next week?
Yeah, I'll be around. Yeah. Yeah, so, if you have any conceptual questions or anything, feel free to come by. Be more than happy to talk to you about it. Okay, so let's get back to, what originally I said I was going to talk about, but then got sidetracked, which is this idea or this kind of more physical interpretation of where do divergences come from, right, in field theory. And the approach that we're going to talk about here is, comes from Ken Wilson, but it's more of a physical look at it. Whereas, what we use, the tools we used before were more, just kind of practical tools that you can use, like dimensional regularization, right? So there we're doing some weird stuff by, shifting into different dimensions, and, we end up with poles and 1 over epsilon, which, what's epsilon, that is kind of more like a programmatic, or I don't know what you want to call it, just a way to extract the poles, right? A simple way to extract the poles and cancel them, right, through a normalization, because you don't care, right? Theory doesn't contain divergences, so you got to figure out some way to get rid of them. All right, but Wilson kind of approaches from a different direction, which is a more physical direction, where you assume, that when you do these loop integrals, you don't do what we do, which was, go off into some other dimension. You physically just cut them off, right? We talked about this in the very beginning of class. How you can introduce a momentum cutoff, and you say, okay, above that scale, I don't know what the hell's going on, right? But below the scale, I can have a pretty good description of physics. It's just when I, try to match the two, I run into some issues as far as computing the coefficients and things, okay? So let's see what we did, okay? So we're going to start with the generating functional, our old friend, right? Still waiting for somebody to get it tattooed on their arm. But if you do, you get extra credit. Okay.
I think I'm good with that.
And so what we'll do is we're basically going to take this guy and we're going to impose some UV cutoff on the theory. Okay. We're writing down the theory and we're saying, okay, we expect this theory to be good up to some value. I'm going to call it lambda, right? And so when we integrate this thing, when we do the path integral, we're only going to integrate for the fields that have momentum below lambda, okay? And everything that has momentum above lambda, we just set it to 0. Okay, we just set those fields to 0. Yeah. So, okay. So that's kind of a drastic way to do it, but you can kind of get a feel of what lies above that scale if you actually do those integrals, right? And you can actually do them, right? So that's what Ken Wilson did. Okay. So what we want to do is we want to compare the result to the original functional integral and determine precisely the influence of these high momentum modes on the physical theory, right? So we're basically going to compute or try to compute those, the integral of the fields in that region, and it'll tell us, or kind of try to understand how it feeds down into the lower dimensional or the lower energy theory. All right, so what we're going to do is we're going to take the normal phi to the fourth Lagrangian, introduce our counter terms, And we're going to work in the on-shell scheme. So this will be like the last time that we work in the on-shell scheme. So I've denoted these couplings and these masses as physical couplings and masses because they're the ones that we measure at the experiment. Right? Remember that in the on-shell scheme. Okay. So what we want to do is basically we're going to compute the 4-point vertex. Okay. And remember that we have some freedom in how we define the exact vertex when we go to renormalize it. And we typically, set the coupling by taking our whatever our expression is and setting all the external momenta to 0, and then compare that with the experiment. And that's how we extract out the coupling. Okay. So we have our normal path interval. And what we want to do is we want to do another one of these Wick rotations, okay? Because it gets us out of this, out of the Minkowski metric into a more Euclidean metric. And what you want to remember is that anytime you do that, now you can start to do these intervals using spherical coordinates, right? So that's what we're going to do. So we're going to take the generating functional, we're going to do a Wick rotation. So there's going to be a change of sign on some stuff because you're going to pull out a factor of I here, right? And it's going to combine with that I, give you a minus sign, and the same thing with the source term. Okay, and now the integration in the action is actually going to be, the time one is going to be along the imaginary axis. Okay. And so our Lagrangian becomes that. So you see that the mass term, or they all have the same sign now. So we have that kind of, that idea that it describes more like an energy, right? We know that there's some lower bound because it can't go negative or can't decrease forever. And because we're in this Euclidean metric, the dot product of the d mu phi has plus signs everywhere. Okay. Right. And so what you see is that in equation 56, what we call the Euclidean path integral, that it's strongly damped. There's no oscillatory parts there because there's no factors of I. Right? It's like an exponent. It's like a dying exponential. Okay. That's another advantage of working with this in this Euclidean space, right? Because we're going to see that it makes we're going to be able to extract the convergence properties of the different intervals that we're going to compute. Okay. So now you say, okay, I did Wick rotation. What do I do now? And whenever we're in doubt, Fourier transform, right? So we can do a Fourier transform because we know we have these derivatives, right? We want to try to simplify this thing, or simplify the path integral, right? Because we want to be able to compute the corrections from the fields that lie above our momentum cutoff. So let's try to take the Fourier transform of the field and plug that in, right? Because what it'll do is we'll be able to rewrite these derivatives in terms of factors of k, because they're going to pull down factors of ik. Okay, so we had to do some integration by parts and throw away any surface terms that we get, and we go through some hellish algebra. So let me see what I'm doing here. So I've done the integration by parts. That allows me to write that phi out in front. Del squared's acting on this phi. I plug in my Fourier transforms, take the derivatives, and then I combine the two exponentials, and then I say, oh, this exponential with this guy is the Dirac, it's the integral representation of the Dirac delta function. So that gives me this delta function, which then allows me to do one of these momenta integrals, right? And so I go from that thing, that mess up there, down to something that looks like this, okay? And you can do the same thing for the phi to the fourth term. You just have to introduce four, Fourier transforms and do the same tricks. You get a delta function, tells you to conserve, four momenta at the vertex or not, okay? But you end up with an action, a Euclidean action that looks like that, okay, in momentum space. All right, and this is the thing that we want to try to evaluate, okay, and so this is where we're going to introduce this cutoff, and by definition, it has to be much larger than any of the physical scales that we have, or any of the scales that we have in our theory, so it has to be much higher than the mass of the particle in this case. Okay, so then what we want to do is we say, okay, maybe we can do these integrals over the field or over the momenta where the momenta is larger than our cutoff. All right. Right. And for convenience, because these modes aren't going to be physical, right? We're not going to have to worry about their dynamics or anything like that. So we can set the source term to 0, and that'll allow us to do the intervals, right? So basically, what we're doing is we're kind of separating out the generating functional because it's all this stuff's in an exponential, so you can always pull it apart, right? And so I've defined something called minus S effective, and minus S effective is related to the Euclidean guy, right? And you see that I've split the integral into an integration from k up to lambda, and then there's a piece that accounts for the k greater than lambda, okay? And it's this S effective, which is called the Wilsonian effective action. All right. And so what you have now is a Lagrangian that not only depends on the field and its derivatives, but its physical parameters are going to depend on this cutoff scale. Right? And the effect of the k greater than lambda part of the integration is going to introduce some new operators, some new terms to the end of the Lagrangian. Okay, and their coefficients are going to depend on the cutoff scale, and they're actually they basically play the role of like counter terms. Okay, we'll see how it comes in. All right, so right, so these are the fields that have that we've cut off the momenta. Okay, the effect of the momenta larger than lambda are these terms right here, these operators. Okay, O, it means operator. Right? It's going to be some combination of fields, basically. Okay, and what is typically, what you typically say when you see an effective Lagrangian like this, with some phi to the fourth or any theory, and then it has some dimension 6 or higher operators. You say that you had some fundamental theory at high scale, and you basically, this describes effectively the theory at a low scale, but in going from the high scale to the low scale, you've integrated out these heavy particles, the particles that have the momenta larger than lambda, the modes of these fields. Okay, does that make sense what I'm saying? Okay, so you start out with some fundamental theory. We don't know what it is, right? But we can imagine, what's happening, and what's happening is as we move down lower in energy, we have things like this, right? So the first term that you have there that's allowed is phi to the sixth, right? And you say, well, wait a minute, where does phi to the sixth come from? Well, it could come from a loop diagram, that looks like this. So you have you've only got 4-point interactions in the fundamental theory, right? Or in the phi to the fourth theory. But you could have fields circulating in this loop that have momenta greater than lambda, right? And when you integrate those fields out, that loop becomes what we would call a 6-point vertex. What to us at low energies looks like a 6-point vertex. Okay, but it originates from loop diagrams like this. Okay, and that was actually the idea behind the Fermi theory of was it muon decay, I think, where he introduced a 4 fermion operator They look like this, right? And this is a non-normalizable interaction, right? But what they ended up finding was, so he used this and, was able to describe muon decay or whatever, W decay, whatever. But what they found was that it was actually, when you go to higher scales, that vertex was actually this, right, where this thing is a W, okay? So if you go to higher scales, you're able to probe, interactions like this, and you might be able to see that, they're coming from these loop corrections, or in this case, the exchange of a W. All right, so you always want to respect the original symmetry, so that's why we can only go with even powers of phi. And like I said, all those coefficients, the mass terms, the couplings, they're all functions now of lambda because we put in this physical cutoff, right? And now what you can do is you can take your theory, you can do all the stuff that we normally do, which is, to compute correlation functions, we take functional derivatives, we can, come up with a scheme to write down Feynman diagrams and Feynman rules. And those rules now are going to include some UV cutoff on the loop momentum, right? So anytime that we do any loop integrals, we're going to have a strict cutoff, right? Because we imposed it at the beginning on the path integral. Okay, that's the difference. All right. So we've done it. So the difference is that before, we started with just the normal. Well, we did phi cubed, but this, in this case, it would be phi to the fourth, and you go and compute loops, and you see these divergences, right? Whereas now, and then you would cancel them off, right? Whereas now, what we're seeing is that we're doing it from the beginning, right? So we're taking the action, and right from the beginning, we're separating out. We're putting this physical cutoff, and we're separating out, the part of the action that, corresponds to low energy scales, and the part that corresponds to high energy scales. And those high energy integrals, we can actually do them. And what we get are these kind of extra terms that you add on, right? These effective operators. All right, so you do all the normal stuff, but now you have these extra terms that you can work with. So if you're looking at, I don't know how to find the sixth term. Oh, if you're going, if you wanted to compute 5 into 4 phi's, right? 5 phi into 4 phi's, we would have, how would you do that? So you would have something that looked like this, and then these guys radiate off phi's or something like that, right? But in our effective theory, we would actually have a term that had 5 phi, and then 2 more phi's coming out of this vertex. Right? We would have some effective Feynman rule for this term. Okay.
That's what happens in higher energy and this one lower energy.
Well, you would put this term in this approach, right? If you were computing this thing. Okay.
That one would depend on the lambda. It would have a lambda.
Yeah, this would, yeah. I have some lambda dependence, right? Yeah, so actually, I think what you're saying is that this would be tree level, and this, I think, would come in at the loop level, right? Because it corresponds to something like some nightmare like that. Okay? Oh, no, wait, it's phi to the fourth theory. What am I doing? Oh, yeah, so this couldn't be. Well, you get the idea. I can't go between phi cubed and phi to the fourth theory. Anything else I want to say? I don't think so. I just wanted to get the idea of, what Wilson's approach was. And you could go on and apply this stuff not only to the full theory, but you can apply it to particular vertices and compute these coefficients, explicitly, right? So you can compute them. They're always going to have some mass dimension in the denominator because why? Because we're talking about higher dimensional fields, right? Or terms with more phi's, right? So in 4 dimensions, phi to the 4th was as high as we could go, right? Because if we go any higher, then our couplings are going to have negative mass dimension, and we know that's not normalizable, right? So in this case, what you're doing is you're adding phi to the 6th, but you need something in the denominator of the coefficient that will cancel out 2 of those factors. See what I'm saying? All right. So in this case, if you wrote down a phi to the 6th term, you would have some 1 over lambda squared in your coefficient.
It comes naturally from the
Yeah. Yeah, when you integrate out the higher modes, yeah, that's where it comes from. It comes from this interval, right? Which is just the propagator, and like I said, integrating from lambda up to infinity. Okay, so it's the effect of the higher modes, and I don't a lot of technical stuff, but I'll just let you guys read this on your own. It's a lot of stuff, a lot of details. But just know that it's a different approach, and it's used a lot in model building because a lot of times you don't want to write down the full theory, right? Because you don't know what it is or whatever for whatever reason. But say you need in the case you need a 4 fermion operator, right? But a 4 fermion operator is not normalizable. So you use an effective theory, and you use these kind of inverse powers of the cutoff to keep it normalized, like in a normalized form. Okay, but you'll see that a lot because that's just the way people do nowadays. They work with effective theories more than they do starting from the top. They do more of a kind of a bottom up approach. All right. So we'll stop it there, and the lecture notes or the notes for what would have been Tuesday, like I said, they're on the website, but you don't have to worry about those for the exam. Okay, just worry about up to this point, and it'll be qualitative, a lot of true false, a lot of multiple choice, fill in the blank type stuff. Okay. All right. All right. See you guys a week from now. But I'll be around. All right.